This is probably the closest we've gotten to a bell-shaped curve this semester. Unfortunately, wasn't enough up on the high side of the bell, but this is what it looks like for this time around. What I have done is I have gone through the grade book and I have set up the grade book so it is now dropping your lowest exam score of the semester. The final is not a droppable exam, it's one that counts for everyone. Now if you want to interpret the score that is on your exam sheet there, it's showing a score out of 104 points, and I've typically been very careful about how they sum together and make sure they sum to 100. They didn't sum to 100 this time, they summed to 104. But in the spirit of giving, decided to basically assign you what would be the equivalent of about 4 extra credit points, or 4 points for everyone. So instead of taking your score out of 104, basically just crossed off 4 of those points as freebies and listed that score out of 100. So if you're wondering what that's all about, that's what it is. I subtracted the number wrong, which is on the bottom right-hand corner of your front page, from 104, which should then show a score out of 104 points, and then, like I said, basically just crossed out the 104, replaced with the 100, and that's the score that you have listed. So, that said, here's what we need to accomplish today. Today and on Thursday. We are going to go through Chapter 10 today and Thursday. Chapter 10 deals with what's called the Vesper model of the atom. And the Vesper model is spelled like this. It's spelled V-S-P-E-R. And it stands for the valence shell electron pair repulsion model. And you're going to find that come the final exam, a lot of these Chapter 10 concepts are actually pretty highly emphasized on the final. So it's not like you say, well, geez, I don't have a separate exam on this, I'm not going to study hard on it. You actually need to learn this stuff very well at the end for a couple reasons. One, because it does have a fair amount of emphasis on the final. Secondly, how many of you are planning on going into Chem 2 next spring? Okay. For you people especially, if you've looked ahead, you're going to see that Chapter 11 deals with intermolecular forces and how atoms interact with each other. In order to talk about how atoms interact with each other, as far as molecules interact with each other with intermolecular forces, you need to understand what we're wrapping up with here at the very end. Many colleges, if they have longer semesters or have a 5-credit course instead of a 4-credit course, will actually wrap up the chapter, wrap up the first semester, including Chapter 11 in those courses. And so what you're going to find come the final exam, there's actually going to be a couple of Chapter 11 topics on there as well. So let me talk about what that final is going to be. There's a handout up here. If you came in late, you can pick that handout up right here. As we've talked about with the final exam is a standardized exam, which means it's one that's administered on a very large scale across the country. Not everybody does it, but probably a significant majority will do these. I know when I went to my national meetings of my chemistry teaching peers, the majority of my peers at the national level do use this exam. And your grade on this exam is going to be based on how you perform relative to your peers at the national level. So, if you read through this, because it is a standardized exam, that means that we have to standardize the conditions so that your conditions are the same as the conditions as your peers taking the same exam. So, that said, this exam is going to be 110 minutes. It's going to be very strictly timed. If you are not done at 110 minutes, the exam is going to be taken from you. You cannot write anything else on the exam from that point forward. There are a total of 70 questions on the exam. They are multiple choice. Since the score on the exam is based on the total number you correct get correct, and that's it. It is to your advantage to answer every question, even if you run out of time. So as you approach that end, if you're still working, you will want to make sure that you at least get something down so you have some chance on getting something correct on the exam itself. Programmable calculators are not permitted on the exam, which means if you're toting around a TI 83 or 84 or 89, anything programmable, it may not be used. I do have some that I can loan out for the exam, but I do not have a full classroom set that can be passed out in here. So what I need to know right now is if you do not have access to a non-programmable calculator, raise your hand very high so I can get a count of who would need to borrow one. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if nobody else is lying in here, I have enough for you, okay? And so I wouldn't sweat it too much. But if you didn't raise your hand and you show up and need one come exam day, I am going to run out. So that's the way it works. Now, if you want a chance at making sure you do have one, the library does have a few on reserve that can be checked out. And so maybe if I was in your spot and didn't have access to a non-programmable calculator, I would be doing the 200-yard dash down to the library and making sure that you beat your peers in the class here at the end of the hour to see if you can check it out. And I don't know how long they check it out. It might only be a day or two, but run down there and you can check with them. But again, otherwise I do have, appears to be about 12 calculators in here that I can loan out on exam day. So with that, then you would notice that there's certain things you are expected to know. Go through this list of things. You're going to see that this is basically a list of things that we have gone through. A couple things that are going to show up that are not a part of this course are these things right here. This is on page 2. These involve stuff from chapter 11. They include intermolecular forces, lattice energy, phase transitions, relationship of boiling point and melting point to intermolecular forces, and such. And you might say, well, geez, that's not fair that we are going to have stuff on the exam that we haven't covered yet, and we won't cover. What I will tell you is that at the national level, your peers are in the same boat. In many textbooks, the chapter on gases appears around 11 or 12, and is a concept that's not covered until the second semester. So there's always going to be something that, depending upon who's teaching it, I mean, the Gen Chem is a pretty standardized curriculum, but there are variations at the national level, and things that we cover or have emphasized may not necessarily be the stuff that have been covered or emphasized elsewhere. There's almost always something left out if you go to the national level. Now, how many of those questions are there? Well, aren't many. Okay, I will tell you that there are some, but I'm giving you the heads up. So if you want to look ahead to chapter 11 and want to know what are those concepts that could be there, they are listed here if you do want to look ahead. And then, of course, you are prepping yourself for the next semester if you plan to be a part of the Chem 1062 course. You're expected to know the formulas that are listed here. And so I say expected to know, that means that these are not going to be provided for you on the exam. So hopefully you should know things like density right now is the ratio of mass to volume. Even though this equation looks to be very complex to find the standard enthalpy change, remember that whenever you do a change in the delta symbol, if we want to simplify it, the delta symbol always means to take the final minus the initial. That's the way it always works. So as long as you just remember to sum together everything for the final, which is the products, and subtract from it the sum of everything for the reactants, which is the initial, you're in good shape. Pivner. If you can remember it that way, Pivner, great. Remember it that way. Here's your one for finding the heat using the specific heat capacity. This one should be one that makes sense. Q system equals negative Q surroundings. That's your law of conservation of energy. So keep those in mind. As far as what's provided for you, there will be a comprehensive list of symbols and abbreviations. It probably will not be as comprehensive as what you'll find on the back side of your periodic table that we've been using thus far, but it is a rather comprehensive list. Likewise, the constants, I think Avogadro's number is probably provided, but if it hasn't, hopefully we've used it enough times to remember that Avogadro's number is 6.022 times 10 to the 23rd. And again, there will be a periodic table provided. As far as the directions go, you are going to be reminded when the day comes that you cannot write anywhere in the test booklet itself. You are going to have available some scratch paper that will be inside of there that you'll do all the writing on there, but you are not to make any marks in the exam booklets themselves. Each question will only have one correct answer and has 4 choices. And again, as we mentioned, your score is based entirely on the number that you answer correctly. It's to your advantage to answer every question. The strategies that are listed here are the same strategies that you should have been implementing any time you take an exam or you feel pressed for time. That is, you do not get stuck on any one problem. If you feel yourself getting stuck, just move on to the next one and then come back to it later on. Your score is going to depend upon your percentile ranking. If you are unfamiliar with percentiles, percentiles and percentages are not the same thing. So if you got 50% on the exam, that's not the same as being in the 50th percentile. If you were in the 50th percentile, what that means is that 50% of the people, you perform better than 50% of the other people taking the exam. So in that case, that means the 50th percentile is average. So if you score at the 50th percentile, that would be like getting a middle C. And if you are at the 50th percentile, a middle C in this course would be the equivalent to scoring a total score of 75%, because our C range is the 70 to 79. So what we've done then, if you go on to this next page, is we've basically translated how the scores work in here. If you are in the 80th to 100th percentile, that means you're in the top 20%. You're going to get an A. If you are in the 60th to 79th percentile, you are in what's called the second quartile. Not quartile, this would be a quintile. And so those people score a B in here. If you're in the 40th to 59th percentile, you'll be in that middle quintile, and you'll receive a C. If you're in the 29th to 39th percentile, you'll be in the 4th quintile. If you are in the 19th percentile or below, you're going to be in the bottom quintile, and you'll receive an F on this exam. So what we've done here is we've looked at the history of this exam, and the history of the exam says that if you want to score in the 100th percentile, which is basically better than everybody else that takes the exam, you need to score a minimum of 64 out of 70 on this exam. So that means you can still miss 6 questions on this exam, and you're still going to be better than anybody else that takes this exam at the national level. Okay, so because you're going to be in the 100th percentile, that'd be the equivalent to like 100% scale percentage. You'll wind up being assigned a score of 200 out of 200 on the final. And so basically what you want to pay attention to is what is your raw score out of 70 that you're going to get over here. If you want to translate it into what does that give me on the final exam, for example, we said that if you're in the 80th percentile or above, you're going to get an A. The breakoff with the 80th percentile is a score between 50 and 51. So it looks like if you score 51 out of 70, that's going to put you at the 82nd percentile, which would be like the lowest possible A you could get. We've translated that into a score of 91 out of 100. And since the final is worth 200 points, we double that, and you will wind up getting a score on the final of 182 out of 200. So read through this table. Any questions on how this table works? Any questions? So some of you are saying, wow, we can miss 19 questions out of 70 and still get and A. Remember, each question only has 4 choices. So if you're a monkey throwing darts, you're going to score 25% on this exam. 25% means out of 70. What's 70 divided by 4? 17 and a half, right? So that means 17. See, there's even a few people that scored worse than the monkey throwing darts over the years. Okay, so it's possible. Hopefully you're not in that position. I think that historically, over all the time that I've given this exam, the lowest score that I recall seeing is a 19. The highest of any of my students has been a 67 over the years. Okay, so if you're shooting for anything, shoot for the 67, not for the 19 on the other end. Okay, so any questions? Done.
I don't see like the date and time for the final listing.
The date and time. Right here. Tuesday, December 12th, a week from today, at 11:50 till 1:50 p.m. We'll actually use about the first 5 minutes to go through instructions and to remind you, like, don't write on the exam booklet and stuff like that. So we'll probably begin about 11:55. It's going to be in, not in S235, it's going to be in S245. This room right here. You do have a review guide, which we passed out. And again, no programmable calculators are allowed. If you've not been through final exams week here at the college before, the only thing that takes place during final exams week is final exams. So we have one meeting next week. That one meeting is going to be on Tuesday the 12th. It's going to be at 11:50 a.m. and it will be for the 2-hour period. Remember, though, that you get a maximum of 110 minutes on the final. Any other questions that you have? Okay, the final exam is going to feature an international convention for writing units. We've mentioned this before, but do want to mention it again. The International Convention does not write units the way that we typically do it here in the U.S. The convention for writing it internationally would be as m dot s to the negative first, right? So all of the units are going to be written on a single line. And so if we had something like, let's see, we had the units for the gas constant, which was 0.08206. Units were liter atmospheres per mole dot K. If we were to write this using the International Convention, we'd write it as 0.08206. Then we'd write it as there you go. Yep. So again, the convention would be we don't write any units in the denominator. This is how we'd write those units out. So that's going to be one thing where you might look at it and say, what the heck? Just as long as you're aware of how these units are written, they will be written as boxed here on the final. Any other questions that you have? Any other questions? All right, going once. Emily?
Could you mention the study guide books name again?
All right. I did not mention it today, but what Emily's referring to, in case you missed that class, down in the library, there's an ACS guide. It might have the word spelled out. ACS is short for American Chemical Society. It's the ACS guide to the general chemistry exam. I forget the exact title. But the library has it on reserve. The book is one that covers a full year exam, which means that you're going to see things that are from the second semester, but if you go through it, and you should be able to identify the questions that are first semester topics and go through and practice those questions that are on there. So I'll give you an idea of the writing style on the exam and what the choices look like and so forth. And that is at the, if you go in the library and ask for it at the front desk there, they keep that ACS study guide. ACS study guide to the general chemistry exam, something to that effect. Okay, anybody else? And they don't let that one leave the library. Okay, anybody else? All right, well today, review sessions, should mention these. I did post this on to D2L, but there are a couple of final exam review sessions. They're held in the Academic Support Center. I know the 1020 ones have already occurred. Did anybody show up?
Yeah, I have 5 kids.
5 show up? Good. So those would have been, the reason why I'm asking Michaela is she's the 1020 tutor, but I don't know who is 1061. When is it going to be? I can't even see them now. Here's one, Sarah. Where's the other one? Up here, Jared. All right. So those are the people that are going to be leading the review sessions. Those are down in the Academic Support Center. And the SC isn't Science Building. It stands for the Student Center, which is where the Academic Support Center is located. Okay, so any questions on those? These are the times, once again, if you want to write them down. It will not only be this class that's invited, all of the 1061 students from all the sections are invited. As Michaela mentioned, there was about 5 that showed up from all the sections. Typically, they tend to be a small group, but for those that like to hang out with their peers and kind of go through a study packet and what are some of the important concepts that we've gone through during the semester, that's the time that they are done. All right, let's get our handouts out. I have, these are ones that we passed out in Chapter 9. They had the table of electronegativities on the front. I do have 2 of these left. I have 1 of these left. Okay, I have none of these left. Okay, so open up that packet though, and in the center we are going to complete those 2 tables here today. And what we are going to be discussing here today, looks like we're at about 12:53. What we're going to be discussing is what's called the valence shell electron pair repulsion model. And I'm writing too big here, so I'm going to have to slide this over. Look at the valence shell electron pair repulsion model. And if we were to underline the first letter of each one of these, VSEPR, chemists often refer to this as VSEPR. And we talk, even though it doesn't quite work out that way, but we refer to it as the VSEPR model. And the VSEPR model is this. First of all, it is exactly what it says it is. And so these are going to involve pairs of electrons that exist in the valence shell. And of course, where is the valence shell located? The outside. So these are going to be pairs of electrons that exist in the outer shell, and it's going to depend on us looking at them as repelling each other. And of course, why are pairs of electrons going to repel each other? Like charges, exactly. Like charges are going to repel. And so, in the VSEPR model, what we say is that the electron pairs are going to repel each other, and when they do so, we minimize the repulsions by placing them as far apart from each other in 3-dimensional space as we possibly can. So that's what the whole that's what today is all based on. We want to minimize repulsions. Okay? Because if we minimize repulsions, we are going to give the atom the lowest possible energy it can have. So again, what it boils down to is minimizing repulsions. The way we minimize repulsions is to place them as far apart from each other as possible in three-dimensional space. So as you came in here today, even though we hadn't talked about this topic, there was a question waiting for you on the Socrative app. The question says that the bond angle is blank degrees when two electron groups are arranged as far apart from each other as possible in three-dimensional space. So one of the ways we can talk about it then is we could look at this. These would be the bond angles, and these would be as far apart from each other as they can put themselves in three-dimensional space. What is this bond angle? 180. It's not 50, okay? Well, it's not 20, it's 180. So again, when you look at this bond angle, this is 120 degrees. So as you complete this table here, what we're going to do then is we're going to talk about the electron group arrangement. We're going to complete this with the number of groups. We're going to give a name to the geometry, and then we're going to write out the structure. So we'll start then by showing the arrangement for two groups. Now these names, many of them are going to be easy. Many will be something that you need to memorize, a little more difficult. What do you call this arrangement?
Linear.
Linear. Right, this one's the easiest name we'll have. This is a linear arrangement. Now when we depict this, what we're going to show is we're going to show a generic symbol. This just means, by generic, what it means is just one universal that can represent any of them. We would show that angle like this. And then I'm going to put these dots out here to represent pairs of electrons. And this angle now is going to be 180 degrees. So now, because we want to model behavior, what I'm going to do is I'm going to use some balloons to represent pairs of electrons. And I'll blow up a couple balloons here. And we're going to start with just two. And I'm going to try to get these to be the same size. And then I'm going to go ahead and tie these together. And we see then in three dimensions, if they would arrange themselves, they're about the same size, they would arrange themselves at 180 degrees to each other. If I go ahead and introduce a third pair, again these balloons are going to represent pairs of electrons. And again we use balloons because the idea in the Vesper model is that we want to minimize repulsions. If we minimize repulsions, that means that those electron pairs, because they repel each other, are going to take up as much space as possible, and that means that they're going to push themselves apart from each other. So now, I'll take a third balloon, which is going to represent a third pair of electrons. I'll tie this in here, and I'm going to add this to the group by tying it in. And then I'm going to shake these balloons up a bit, try to get them to arrange themselves as far apart from each other as possible. And so now if we look at this here as being the center of the atom, where they're tied together here, notice now that all of these lie on one plane. There we go, and they did. And in three dimensions, if we would arrange them, they would be sitting at that angle that you are going to answer next. So if we have three pairs, or three groups, around the central atom. Where do we have it? Here we go. Around the central atom. What would that angle be? What is that bond angle if we have three groups around the central atom? try to tie this a little better so they stay together. There we go. And if you're looking for a name for this, trigonal planar, good. So 3 groups. We call it a trigonal planar arrangement. And as far as the bond angles go, let's see how we did. Correct answer here is 120 degrees. 120 degrees is the correct answer. So the way that we would write that, we would put in our central atom like this. We then show 3 pairs around the central atom. Of course, why is it 120 degrees? 360 divided by 3, exactly. In a circle, there's 360 degrees, which means that these bond angles here would be 120 degrees. If we go on to 4 groups. Now again, I'm going to bring in another balloon into this arrangement. Looks like about right. I'll go and tie this up here. And then we'll put this into the mix. I'll try to do this now without getting the rest of them to fall apart. So now if I shake this up here a bit and we set it down, we see that we have something that looks like a tripod with 1 balloon on top. Move it like this, it looks like a tripod with 1 balloon on top. Tripod with 1 balloon on top. Tripod with 1 balloon on top. And that would be this arrangement right here, because again, if I arrange this, no matter how I arrange it, it should look like a tripod with 1 stick up. Now, if we put and drew imaginary lines between each of these vertices, that is from here to here, here to here, here to here, we start connecting them all together, how many sides is that object going to have? There's 1 here, 1 here, it's going to be 4. The face of each side is going to have what shape? And what type of triangle?
Equilateral.
Equilateral triangle, which means all the sides are equal. What do we call a 4-sided polyhedron? Tetrahedron. So we refer to this shape as a tetrahedral shape. Okay, now if we were going to draw this, no, wait, before we draw it, we need to find out what you think about bond angles. What do you think are the bond angles in here? Ooh, now we're dealing with 3 dimensions, not 2.
Oh, that's
So now you got to think, is this going to be more or less than what I'd find in a trigonal planar? What would it be? And let's get your answers registered here. We'll count down 5, 4, 3, 2, 1. I see 2 correct answers in here.
109.5.
I see 3 now. It's 109.5. 109.5 degrees. So whoever got them, great job. Yeah, now how do you even know that? I don't know how you know that. Okay, so now, if we want to represent this, we're going to show 1 going up. And now we're going to learn about 2 different types of projections. One of the projections is going to be one that projects outward and one that projects back into the paper. These 2 here are going to be on the plane of your paper. So if you look at this as being the plane, you're going to have one projected out, one projected back. To show one that projects out, we use a wedge. That shows it's coming out towards you. And to show it projected back into the paper, we draw in a dotted line. So it goes something like this. We draw a wedge out like this to show what's being projected out. We show a dotted line to show the one that's being projected back into the paper or your screen or whatever you're looking at there. And then the line here is one that is on the plane. So again, as you look at it, these two here are on the plane of your paper. It's on the same plane as your central atom. There's one that's projected outward, which we show as a wedge, and one that's projected backward, which is going into the paper. And again, all of the angles in this case are at an angle of 109.5 degrees. Now if we go on to 5 groups. 5 groups. I'm going to go ahead and put another balloon here into the mix. There we go. We'll go ahead and tie this up. And we'll put this balloon into the whole mix and grab it all in here. Yeah. All right. Find one of them here to tie onto. There we go. Shake this up a bit. Turned out all right. It's not quite perfect. I need to push them there a little bit. Here we go. So now if you look at these two, look at these angles relative to each other, and then look here in the center. Notice that all of these in the center pretty much lie on one plane, and then the two that I'm holding are at what angle to each other? 180. So if these are 180 to each other, what angle are they to the central plane? 90 degrees, right. So you have. Any other questions? All right. So I would say that probably, though, the one you asked about is the one that students have the most difficulty with, and that is what is the bond angle. So just the new one for most of us is going to be the tetrahedral of 109.5. All right. We go on to the next one. We're now going to draw out some structures. And to do this, we need to introduce some vocabulary. The vocabulary we're going to introduce looks like this. First of all, we're going to talk about the electron geometry. We say that the electron geometry is the geometry of the electron groups around the central atom. Whether they are lone pairs or bonding groups. And by bonding groups, we mean either single, double, or triple bonds. So again, the bonding group could be a single bond, it could be a double bond, it could be a triple bond. And so if we're talking about a triple bond would still count as one group. Even though there's 6 electrons, a triple bond would count as one group. In a double bond, even though there's 4 electrons, a double bond would still count as one group. What we just looked at back on this table, these are the electron geometries. These are the electron geometries. What we're going to look at next is what's called the molecular geometry. And if we look at the molecular geometry, we say that the molecular geometry is defined like this. We say it is the arrangement of atoms the arrangement of the atoms in a molecule or polyatomic ion. So it's kind of a misnomer when we use it with a polyatomic ion. And by misnomer we mean that it doesn't really match what it is. Because we should be talking about a polyatomic ion geometry, but we still use the term molecular geometry even though we're not talking about the molecule. Now, one example I'm going to give is going to be H2O. Okay, so let's look at an example of H2O. Now let's draw out the Lewis diagram for H2O. So if we draw out a Lewis diagram for H2O, we've done it first of all by saying how many valence electrons does each hydrogen have? It's 1. And so again, if we're looking at a periodic table, we have each hydrogen with 1, and the oxygen atom has how many? 6. So we have the 1 valence electron for each of the hydrogens. We have the 6 for the oxygen. Altogether, we have a total of 8 valence electrons. So now if you were to draw this out, you would then have drawn it out up to the stage, something like this. Okay, now, when you drew it out, I can't even remember for this class because we've gone fast enough this semester. We may have told you at this point that when you draw a molecule of water, just always draw it bent. I don't know that we talked about the reason why though, did we? Okay, so here's the reason why. First of all, if you drew out its structure, if you haven't been drawing it bent, you've been drawing it incorrectly thus far. It's supposed to be drawn like this here. And so now if we look around a central oxygen atom, if we look at this as being oxygen right here, even though I know if you do these kits in lab, it's black, represents carbon, we're going to say that this represents oxygen. How many groups of electrons are around this central atom? There's 4, because these lone pairs each count as an electron group, and each of these bonds count as an electron group. So around the central atom there should be 4 groups of electrons. Now we would say that that electron pair arrangement, electron group arrangement around the central atom is a tetrahedral arrangement. Now again, 2 of them are going to be taken up as bonding pairs. 2 of them are going to remain as lone pairs. And so if I use 2 of these up as bonding pairs, what we wind up with is the shape of a molecule that is bent, because in 3 dimensions, these 2 groups still take up space and are going to repel each other. Now, if the question to you was, what is this angle in here? What is this angle right here? Now I know you'd love to say 109.5 because after all, that's what we just learned, right? But it's not 109.5.
120.
How much?
120.
It's not 120 either. It's actually 105 degrees. Now, here's where that comes from. You do not need to memorize the 105. You need to learn the 109.5 that we talked about. What you should know is that this angle is less than 109.5. I know that it's 105. If you want to memorize that trivial piece, you can do it. Okay? That'll only be useful to you if you're going to be a chemist. All right? But you should know at least that it's less than 109.5, and here's the reason why. If I asked you now which pairs or which groups of electrons are held more closely to the central atom, is it going to be the lone pairs or is it going to be these bonding pairs? The lone pairs are going to be held more closely to the central atom because the lone pairs belong to 1 atom. The bonding pairs belong to 2 atoms. So because these lone pairs only belong to oxygen, that means that oxygen is going to pull those closer to the central atom. If it pulls it closer to the central atom, what is that going to do to the repulsions? It's going to increase them because, remember, like charges will repel. If it brings it closer to the central atom, that increases repulsions. That means it's going to do what to this other bond angle? It's going to go ahead and squeeze the gap a little bit. It's going to squeeze them together, and as a result, this bond angle is going to squeeze down to be something less than 109.5. So, what you need to know here is that this angle is less than 109.5 degrees. If you want to know what it is in water, I'm telling you it's 105 degrees. You do not need to know the 105, but again, you should know that it's less than 109.5, and you should know the reason why. And again, the reason why, which pairs of electrons are held more closely to the central atom? Lone pairs. Because they're held more closely to the central atom, what does that do to repulsions? Increases the repulsions. If it increases the repulsions, that means it's going to push this bond angle closer together. And that's how it will always work, is that the lone pairs will always push the bond angles in a little bit closer, a little tighter than if they are by themselves. So, going on then, any questions with that? All right, so for the next ones, we are going to draw out some representative structures, and here are the ones that we are going to draw out. Oh, and they are here. So the first thing we're going to do is, let's write out a Lewis structure for the nitrate ion. Let's write one out for carbon dioxide. Let's write one out for xenon tetrafluoride. Let's write one out for ammonia, and write another one out for sulfur tetrafluoride. And I might have called this one wrong here. This is xenon tetrafluoride. So do these the way that you would have always written them out. Don't worry about resonance today. Just draw them the way that we initially drew out those Lewis structures. If you need to pull out your rules, I think I have 2 copies of the rules left. In case you've forgotten them, though we did just get tested on them. I do have 2 copies of the rules left. Anybody need rules drawing structures? This is our handout for Chapter 9. And I'm going to intentionally draw things with the wrong shape. Once again, we are not worrying about resonance. Right now I'm not even drawing the correct structures up, because you're going to help me fix what we see here. let's look at the first three. Let's look at the first three. And that's probably all we'll have time for here today. So, first column here now, what we're doing is we are writing out the Lewis structure for the indicated species, and as we would have done for your exam that you just had. Now, this is not the correct one here for the nitrate ion. What would I need to do to make this one correct? Double bond. Which one should I take? Any one of them. It doesn't matter, which means this one's probably going to have resonance, but we're not worrying about resonance today. So we'll go ahead and shrink that down just a bit. What else does this one need? Right, needs those square brackets there. And what else? Charge out here. Okay. Now, if we go down to carbon dioxide, and this one's not quite done yet, what do I need to do to fix this one? Double bond here. How about the other one? Double bond as well. There we go. And that fixes that one. On the xenon tetrafluoride, I have 4 electrons left to go. Where do I put those 4? On the xenon. And how do I put them in? 2 and 2. Okay, let's do these 3, and then we'll see where we sit on time. I think we'll probably run out. The next thing we need to do here is to determine the electron geometry. Now, we're going to do that based on what we came up with right here, and then we're going to count electron groups. Now, remember that when we count electron groups, that electron group is either a lone pair or a bonding group. And if it's a single, double, or triple bond, it still counts as one group. So if we look at this one here, how many groups are there around the central atom? There's 3 groups. So again, there's one bond here, and a double bond here. So that's 3 groups around the central atom. If there's 3 groups, then we would call that a trigonal planar arrangement. So that's how we determine it. We count the total number of groups around there. We'd say that the electron pair arrangement is trigonal planar. And if we go to the carbon dioxide, how many groups are there around the central atom? 2. There's 2. So if we come back to this here, if we have 2 groups around the central atom, we say the arrangement is linear. So I probably didn't do a very good job of drawing this one out, is what that's suggesting. Okay. Then if we go to the xenon tetrafluoride, how many pairs are there, how many groups are on the central atom?
6.
There's 6. And so if there's 6, we say that that arrangement is octahedral, right here. So we go ahead and fill in the octahedral. Next thing we want to do is to figure out the molecular geometry. And the molecular geometry tells us the actual arrangement of atoms in the molecule or in the polyatomic ion, as is the case here. So if we have 3 groups around here, we have 0 lone pairs and 3 bonding groups. That means that if I put atoms onto this one right here, there'd be an oxygen here, and an oxygen here. And if we now look at the arrangement of atoms in this model, we would say that arrangement is a trigonal planar arrangement. So the name of the molecular geometry is the same as the name of the electron geometry. So when we talk about the molecular geometry, we're looking at the arrangement of the atoms in the molecule itself. So in this case here, we say that its arrangement is trigonal planar. And as such, then, we draw out its structure. To draw it out, then, we put the nitrogen in the center. And now, what angles should we be showing in this model? 120 degrees. So now, what column D says, redraw the Lewis structure to reflect the correct molecular geometry. So if you're wondering why for exam, for chapter 9, as we were going into exam 3, why I was drawing them with this shape. That's because what I was doing was trying to reflect the correct three-dimensional geometry. So I'm not going to get a protractor in there, and if you come up with 115 degrees, mark it wrong, anything. But you want to do your best to draw the bond angles to the best of your ability. So now if we go to the carbon dioxide molecule, we said that there's two bonding groups in this one, which is a linear electron pair arrangement. We go ahead and place some atoms onto here. When we place the atoms onto here, the arrangement of atoms in this case is going to be one that is linear. So we would describe its molecular geometry as linear. And then we draw our molecule as linear as well. So again, I probably didn't draw it very well over here. We are now drawing it with its correct geometry. And that correct geometry for CO2 then is as a linear molecule. Now things get to be a little more interesting when we get to the xenon tetrafluoride. Because now if we get to the xenon tetrafluoride, we have counted around here and we found the 6 groups of electrons. We go ahead and put on the fluorine atoms and start taking a look at what that might look like. And so I'll put on 1, 2. We'll take off 3 and 4. There's a couple different ways this could wind up looking. One of the ways this could wind up looking is just like this. And now notice that if we want to describe the molecular geometry, we would say that all of these atoms are on the same plane. The description we would give to this as its molecular geometry is square planar, if this is correct. Now we could wind up having another shape that looks something like this here, where it looks kind of like, I don't know, maybe like a seesaw type thing, okay? But now, if we want to know which of these is correct, here's what we need to do. We need to remember which pair of electrons are held more closely to the central atom. Is it going to be the lone pairs here, or is it going to be the bonding pairs? Lone pairs. So the lone pairs are going to need as much space as possible. So if they need as much space as possible, we have this one arrangement here where these lone pairs are at 180 degrees to each other, or 90 degrees to the plane. Or we could have this arrangement here, which put these two lone pairs adjacent to each other. Now, if they are adjacent to each other in this position here, because these are both held more closely to the central atom, they are going to want to repel each other more, and they're not going to want to occupy the space where they are adjacent to each other. Because again, because they're held more closely, that's going to cause an increase in repulsions. So the best way to place these relative to each other would be, now I'm trying to get these back out here. Which one am I going to move? This one right here? Yeah, there we go. So we go ahead and move this one, bring it back here, and now these lone pairs wind up having more space. And so the arrangement that we wind up describing for these here is going to be a square planar arrangement. And we get the square planar because when we describe the molecular geometry, we aren't looking at the lone pairs, we're simply looking at the arrangement of the atoms in the molecule. These all sit on the same plane, and they represent a square. So again, the arrangement is going to be a square planar arrangement. Now the way that we draw that is like this. We put the xenon in the center, and now if you think about how we drew this out, we show the two of them that are being projected outward, and we want to show the two of them that are being projected backwards into the paper. So we show the two atoms being projected outward. So we'll project these out to the fluorines. Then we'll have two fluorines that are being projected back into the paper. And then we have the two lone pairs, which we represent like this. And then we can go ahead and put in the extra electrons. and putting in the extra electrons around the fluorine, it winds up looking like this here. But again, when we're talking about the molecular geometry, we're not looking at these here. We draw them in as part of the Lewis structure. When we're talking about the molecular geometry, we're just talking about the arrangement of the atoms in the molecule. And that's where the square planar comes from. So now, in terms of how do we know this, what I've done, this was one of the things I did on my sabbatical a couple of years ago. I happen to have drawn all of these out and have plotted them in 3 dimensions. And so they look something like this. So we have the CO2. The carbonate is going to have a very similar structure. And again, if you want to play around with these, you can move these around in 3 dimensions. We have the xenon tetrafluoride, I think, which is right down here. You can see how they all sit in one plane. But here are the arrangements then that you'd look at. So if you want to look at the molecular geometry, here's how you'd use this table. And this is linked, you'll find this 2 places. One of the places in your textbook. Anybody have their textbook handy here today? Here's mine. So here's where you're going to find this stuff. In chapter 10. And I'm trying here to end on time. You're going to see this on page 436. Page 436. And actually I've combined the table on page 436 with the one that appears on 439 and where? I don't know. Further on, 450 something. 458. So the table that you see here online is one that I'm going to post to D2L. I think it's probably already there. And combines the tables on page 436, 439, and 458. You will need to know that table. We haven't covered the stuff on page 458. That is for Thursday. But what you need to know now is what is the electron pair arrangement, how that corresponds to the number of groups. We've talked about bonding groups and lone pairs and molecular geometry, and we've given some examples. So if we look at the ones that we just looked at here today, we had xenon tetrafluoride, which has an octahedral arrangement for the electrons. It has, if we look at the label of these columns, which is bonding groups and lone pairs, it has 4 bonding groups and 2 lone pairs. So as you interpret the table, 4 bonding groups, 1, 2, 3, 4, and 2 lone pairs, and then lines up with the geometry. Now we're not going to look at all of the examples that's in this list. You will, however, need to know it come your final exam. What I'd like for you to do for Thursday is this. I would like for you to complete these last few answers right here. See how you did. Use the table on page 436 or the one that I posted to D2L. And I know I went over about 1 minute. I'm sorry. So, any questions? All right, so for Thursday, please have these done if we want to end early on Thursday. Have these done, please.